Hi, hello everyone. Welcome to my YouTube channel SRU Motivation for Future. In last lecture series, I have discussed about buck converter operation as well as boost converter operation. Along with that, boost converter design and capacitor design, which I have discussed in the last lecture. Now, in this lecture, what I am going to discuss about how buck boost converter will be designed and why we need to consider the buck boost converter, and along with that, by boost converter, inductor design, capacitor design, how we are going to do all those things I will discuss here. First, foremost thing is what is buck boost converter. In last class, which we have discussed that buck converter. What is the main concept of buck converter? It is nothing but it will step down the voltage from source voltage to load voltage. Step down is happening. Now coming to the boost converter, it will step up the voltage from one level to another level, that is called boost converter. Now in this buck boost converter, what is going to happen? It is going to happen step down as well as step up based on the requirement. It may be doing buck converter operation as well as boost converter operation. What I need to say that buck boost converter, it is nothing but it will operate in both the direction based on the duty cycle of the circuit. So now we will see how buck boost circuit will be designed and what is the structure and what are the waveforms we will see now. Now coming to the waveforms which we observe, that what are the waveforms here which we will observe here, how we are going to indicate. First, first let us see why we need to refer buck boost converter circuit here. Few features of the buck boost converter which I have indicated over here. First is buck boost converter is a DC to DC converter that increase or decrease based on the necessity of the supply. That is the first point already I have discussed in the previous slide. Now coming to that, this is the step down based on the necessity. It will step up or step down. And coming to that, it will operate efficiently for wide range of voltages. Any range of voltage, input voltage, output voltage, this will be applicable. And for the battery charging of the electrical vehicle system, and it provides higher efficiency for electrical vehicle system and design lightweight also. It is possible by using this buck boost converter. And meanwhile, this buck boost converter are using in battery operated electrical vehicles and as well as solar operated electrical vehicles, as well as consumer application. Many applications we are using this buck boost converter circuit, because the reason in a single circuit we are going to do buck as well as boost converter circuit. That is the major thing which we can observe here. Now coming to the next, we will see what is buck boost converter circuit structure. First, we will see buck boost structure. How buck boost converter circuit. Let's see circuit. Buck boost converter circuit. First thing is we know that what is the buck boost converter. First thing is we know that. Wait, I'll draw the diagram in a very clear manner so that you can understand the concept very clear. First, we will draw the circuit diagram, that is VDC. Let us take it as a, this is source voltage, and after that there is a switch. Let us take it as a, this is the switch, and after that there is a, what is there? After that there is a inductor, and after that there is a diode, and after that there is a capacitor, and after that resistive load, which we have to indicate over here. Resistive load. This is the structure of the buck boost converter circuit. This is the switch. It will be any switch. Let us take it as a S. That is called switch. And this is the diode, which we will indicate here. This is plus, this is minus. This is the inductor. This is plus, this is minus. This is the capacitor. This is plus, this is minus. This is the resistor R naught. This is plus, this is minus. Let us take it as a current flowing through the resistor, that is I naught. Current flowing through the capacitor, that is IC, and diode current will be ID. Like this way we have to indicate. Now this is the source voltage VDC, plus minus we can take it over here, and here there are two modes of operations are going to be happened in this converter circuit. First, mode 1 we will take it as a mode 1 operation, that is switch is on. When switch is on, what are the condition we can observe? When the switch is on, inductor starts charging. Inductor starts charging. Diode D will be open circuited. Diode D will be open circuited. And here we can observe that when the switch is on, what is happening? Diode open circuited means current ID is equal to 0. And along with that, Vd is equal to Vi. We can indicate that one. And along with that, if we observe that, what is the thing we can observe here? Vd is equal to Vi, and as well as VL is also, that is source voltage, that is VL is equal to Vi. That those things we can indicate here. Now mode 2 operation. This is mode 1 when switch is on. Now coming to mode 2 operation, that is when the switch is off. What is the switch off condition? When the switch is off, what will happen? Whatever the inductor it is there, it will deliver the energy. It will deliver the energy. And along with that, here capacitor starts charging, as well as load power consumption will happen. Now coming to that, what is happening here? ID is current flowing through that is equal to ID is equal to IL. It is happening here. And coming to that, in this condition, what is the VL voltage, that is equal to VC? We can take it over here, and along with that, I naught is equal to V naught by R. These are the fundamental condition under mode 1 operation as well as mode 2 operation of the circuit. Now, when we are going to derive the average voltage gain of the circuit, we have to remember two things, which are first, under switch on condition, what are the voltage values and what are the load voltage values, everything we will see now. Now, when the switch is on, let us talk about derivation of the voltage gain. Here, what we are going to derive? Voltage gain derivation. How we are going to derive, we'll see. Now under switch on condition, what is the voltage? Kirchhoff voltage law, based on the Kirchhoff voltage law, minus VDC plus VL is equal to 0. Then what is the VL? VL is equal to VDC. Here we know that this is, let us talk about equation number 1. Let us take it as a equation number 2. And we know that VL is equal to L into di by dt. Here, switch on condition, it is nothing but dt is equal to, what is that? T on. And di it is nothing but delta IL. That is equal to I maxima minus I minima. Then equation number 4. From equation 4, what we can write it over here? VL, that is nothing but L into delta IL divided by T on is equal to, how can we write it here? That is equal to source voltage VDC. From this, delta IL is equal to VDC into T on is divided by L. Let us take it as a, this is equation number 5 and this is equation number 6. So like that we are going to derive. Now this is the T on condition of the ripple current, that is delta IL. What I written here, delta IL is equal to VDC into T on is divided by L. That is the first condition which I have indicated over here. Now coming to second condition, we'll see. When the switch is off, apply the Kirchhoff voltage law for the circuit. Then that is the case, what we can write it here? VL minus V naught, that is equal to 0. Then here VL is equal to V naught. Here what I know, as we know that we indicated L into delta IL is divided by, what is the condition here? T off, that is T off L into di by dt. That directly I written over here. Instead of that, you can write it over here also. L into dIL by dt, that is equal to V naught. Like this way you can write it. Now from this, how can we write it this? From this, how can we write delta IL, that is equal to L into V naught is divided by L into V naught is divided by, how can we write it here? So 1 minute, I will indicate in a clear manner. Here, what is delta IL? We can write it here. V naught into T off is divided by, what is that? L. This is under switch is off condition. Previously that is switch on condition. This is switch off condition. Equating both the equations of the inductive ripples, then we will see what is going to happen. Now when we are going to equate both the sides inductive ripples, what will happen here? We'll see under switch on condition as well as switch off condition. See, this is T on condition. VDC into T on is divided by T off, that is equal to next what is happening here? We will indicate over here delta IL, that is VDC into T on is divided, sorry, we need to indicate L value, right? So then that is the case. VDC into T on is divided by L. Next, V naught into T off is divided by L. That thing we have to indicate here. That is equal to delta IL. Here, L is going to cancel out. Then that is the case. We need to derive the output voltage. That is V naught is equal to, what is V naught? VDC into T on is divided by T off. As we know that total time duration T is equal to T on plus T off. Here T off, it is nothing but T off, that is equal to T minus T on. From the resultant, how can we write this one? V naught, that is equal to VDC into T on is divided by T off means T minus T on. That is the thing we have to write it over here. Then these things make it a common as T. Then VDC T on by T is divided by, what is there? 1 minus T on by T. So as we know that, what is the formula for alpha duty cycle duty? That is equal to duty cycle alpha is equal to T on by T. From this, what we can write it here? So when alpha is equal to T on by T, then V naught is equal to VDC into alpha is divided by 1 minus alpha. This is the buck boost converter output voltage. From this, how can we write the voltage gain? That is output voltage is divided by input voltage, that is equal to alpha by 1 minus alpha. Here, based on the variation that is called duty cycle variation, the output voltage either it will be in positive or it will be in negative. Suppose buck boost converter will give note, indicate the note. Suppose buck boost circuit will give negative voltage, then what we can say that the circuit will work as a inverting converter circuit. That is the final conclusion, we can say that. Now, after this, how we are going to design the inductor value and what is the ripple content? It is nothing but same derivation previously, whatever the way we have mentioned, same thing we have to mention the thing here also. Now, how I am going to derive that? What is the uh, inductor value and what is the how it is going to derive the inductor value for switch on time, switch off time? How we are going to derive? We'll see now. Now, when we are going to derive the inductor derivation, let us take it as a inductor derivation. First, when we are going to derive the inductor, we have to note that all the internal resistance that is equal to 0. And next one, utilized inductor and capacitor values must and should be very high. Then only we can calculate the conditions. Next, third one, we have to know that source power that is equal to load power. Then what we can write it here from the input switch on condition, VL is equal to VDC. As we know that VL, it is nothing but L into delta IL by dt. that is equal to di by dt that is equal to VDC. From this, how can we write the inductor formula? L is equal to VDC into T on is divided by L. That is equal to, how can we write it that? L, it is nothing but, here we have to write it delta IL. Here we have to write delta IL. So this is the inductor formula when it is under switch on condition. Similarly, under switch off condition, how can we write the formula? That inductor voltage that is equal to load voltage. Then that is the case, how can we write here? Same manner, L into delta IL is divided by T of into V naught. From this, how can we write? L is equal to V naught into T of is divided by delta IL. Like this way, we will derive the inductor for the boost converter circuit. Now, in the coming lecture series, we will see how we are going to derive the capacitor, and along with that, we will see some numericals. I hope you people you understood the concept. We'll see in the next class. Thank you.